Our ancestors built things we still can't fully explain. Modern engineering looks at them and can't quite figure it out. Civilizations without computers, without steel, they moved stones heavier than locomotives. They built structures that have stood for thousands of years, and some of ours crumble in decades. There was a secret knowledge there, a lost genius. This is a countdown of 20 ancient feats, 20 engineering marvels. They challenge everything we think we know about the past. Which forgotten masterpiece holds the greatest secret? You'll see human history in a new light by the end. Their ambition was enormous. That's the first thing you notice. These weren't people building simple shelters or monuments meant to last a few lifetimes. They were thinking in terms of millennia, building with a kind of permanence that feels almost alien now. To understand what they did, you have to forget our world. Forget power tools, cranes, digital plans. Their world was stone, wood, rope, human ingenuity, and simple machines. The lever, the inclined plane. Knowledge wasn't in books or on a drive. It was in the hands of master builders, passed from teacher to apprentice, generation after generation. That oral tradition worked. It was incredibly effective. But it leaves no paper trail, nothing for us to read. We're left with the silent results, these monumental things, and the task of reverse engineering how they were made. So archaeologists and engineers, they become detectives at these sites. They face specific problems. Dating a structure can spark debates that last decades. Because carbon dating might tell you when a tree was cut, not when the wood was placed. Analyzing the materials opens another mystery, finding stones that were quarried miles away, with no obvious way to move them. But the biggest puzzle is the lost techniques themselves. How did they achieve that precision without modern tools? How did they coordinate hundreds of workers without radios, without detailed plans? Each question leads you back to the same place, a deep respect for their resourcefulness. When you understand the constraints they worked within, their accomplishments change. They go from impressive to seeming almost impossible. That appreciation is essential. It's the foundation, and it frames the first marvel on the list, the most iconic one, a place where stone defies gravity, where history whispers from every perfectly fitted block. That's the Great Pyramid of Giza, a monument built to last. It's been there for 4,500 years, just dominating the skyline. The scale is hard to grasp, over 2 million stone blocks. Each one averages 2.5 tons. Some of the granite inside is closer to 80 tons. But the real thing isn't the size, it's the precision. Modern engineers with lasers have measured the joints between those limestone blocks. The gaps are often less than 0.5 millimeter. You can't slide a piece of paper in there, you can't slide a credit card, and you have to think about that. Stones the size of small cars, quarried miles away, dragged across the desert, and placed with a fit that rivals a machine shop. They did that millions of times. So how? That's the question. The classic idea is thousands of workers dragging blocks up enormous ramps. It seems logical. But the engineering a ramp to reach the top would have needed more material than the pyramid itself. A mountain next to a mountain. Other theories say an internal spiral ramp built inside the structure as it grew, or maybe a system of water locks and canals to float the blocks into place. Each idea has merit, and each one has its own logistical nightmare. Moving the stone is one puzzle. Placing it with that hair's breadth accuracy is another mystery entirely. They had no steel tools, no precision levels like we have. Their main surveying instruments were probably simple plumb bobs and sighting rods, and yet they aligned it to true north with an error of just 3/60ths of a degree. To put that in perspective, the drift we call magnetic north moves more than that over time. Their north was essentially perfect. That points to a deep understanding of astronomy. Watching the stars not for myths but for geometry, The pyramid is a machine built from stone and celestial knowledge. It's a single, perfect answer to a question we're still learning how to ask. And it makes you wonder, if they could align a mountain to the stars, what other impossible alignments did they manage? That celestial alignment wasn't just in stone. It was in bronze too. You go from these huge, still monuments to this intricate, moving machine. It feels like a jump in time, but there was a shipwreck off a Greek island. Divers brought up this lump, all corroded bronze and wood. That was the Antikythera Mechanism. When they found it more than 100 years ago, it just looked like a rock. Covered in sea life, but inside that rock was a precision instrument, a clockwork universe in a box. X-rays showed what it really was. It wasn't a simple calendar. It had over 30 bronze gears, all interlocking. Some of the teeth were so fine, barely a millimeter thick. It was an analog computer. It predicted where the sun and moon would be, and the planets. It could forecast eclipses. It even modeled the moon's irregular orbit, which needs a kind of gearing, differential gearing. Engineering books say that gearing was invented in the 1600s. For cars, this device had it 2,000 years earlier. So who built it? The best guess is the Hellenistic thinkers, maybe inspired by Archimedes. It was a tool for philosophers, for navigators, for reading the sky, but to build a replica with the tools they had, that's the puzzle. You have to hand-cut every tiny gear tooth perfectly. You have to align them on axles in a wooden frame. A single error, a fraction of a millimeter, and the whole cosmic calculation is off. It's a different kind of genius, miniaturization, complex systems. It shows ancient innovation wasn't just about moving mountains. It was about modeling the heavens in your hand. And if they could build a machine this sophisticated to track water in the sky, what could they build to control it on the ground? The sky works as a clock. The sea is a road. In the ancient world, water was the highway. To master that water meant you mastered trade. You mastered travel. You mastered time itself. The Greeks built a machine to chart the heavens, but another civilization engineered the earth to command the water on it. That was the Incas in South America. What they built feels less like a construction. It feels more like a negotiation with the landscape. At the heart of their empire, high in the Andes, they built Machu Picchu. And the real marvel isn't the stone city on the ridge. It's what's underneath. The entire mountain is terraced, but these aren't simple farm plots. They're a massive drainage system. Intricate, each terrace is a layer of stones, then gravel, then sand, then topsoil. Water from the mountain rains filters down through these layers. It prevents the soil from washing away. It keeps the foundation stable. The stones are fitted together without mortar. They shift and settle with the earth during tremors. They lock themselves tighter. They built for earthquakes. They understood that to survive there, their structures couldn't be rigid. They had to be alive, in a sense, able to move. To adapt, that's a philosophy of engineering that thinks in centuries. It anticipates the very forces that would destroy another design, and it stands in contrast to another ancient material. One famous for its rigidity, but one that has a secret, almost biological, ability to endure. That idea of building to move, it's there in stone all across their empire. You see it perfected at Sacsayhuaman, the fortress above the Inca capital. The walls there are like a puzzle made from boulders, huge ones, some over 100 tons. They're these irregular, polygonal shapes. A single block might have 12 different angles, and they're fitted together so tightly you can't slip a knife blade between them. No mortar, no cement, just gravity and geometry holding a fortress together for 500 years. In a place with constant, powerful earthquakes, these walls don't just stand. They dance. A rigid wall would crack and fall when the ground shakes, but these interlocking blocks, they shift, they jiggle, and when the tremor passes, they settle right back into that perfect, immovable fit. It's like the wall breathes with the mountain. How they did it is a deep mystery. How do you shape granite, one of the hardest stones, with that kind of precision using just stone hammers and bronze tools? The usual answer is abrasion, rubbing stone against stone with sand and water. But to get that fit on that scale, with blocks that massive, that would be the work of generations. Some indigenous traditions talk about a plant juice that could soften stone, a lost botanical knowledge. Others, more speculative, suggest sonic levitation using sound to make the stones lighter, easier to move and place. Whether it was a forgotten technology or just an unimaginable mastery of simple tools, the result is the same. They turned brute stone into a flexible fabric. They built structures that were partners with the land, not conquerors of it. And that harmony between human creation and the natural world, it finds its most dramatic expression not in a wall, but in a city carved straight from the living rock. The Nazca Lines are in southern Peru across this dry plateau. They're not something you can walk up to. They're drawings, but on a huge scale, made by etching the dark desert surface to show the lighter earth below. Some are just lines, perfect, straight lines that go for miles. Others are shapes, a hummingbird, a spider, a monkey with a tail that spirals. They're geoglyphs, so big you can only see what they are from way up high. And that's the first part of the mystery. The Nazca culture made them between 500 BCE and 500 CE. That's long before anyone could fly. So how did they design something they could never see? The challenge is perspective and permanence. They used simple tools, probably wooden stakes and rope. To make a straight line over a hill, they'd set up sighting posts, keep the path true across the uneven ground. For the figures, the complex ones, they might have scaled up a small model. Used a grid system, transferred the design step by step onto the desert. But the real clever part is the surface itself. They didn't just scrape rocks away. They took off the top layer of dark, oxidized gravel, exposed the lighter, clay-rich soil underneath. That created contrast, but it did something else too. The exposed layer, packed down by people walking on it, formed a kind of crust, a protective crust, and with the climate there, almost no rain, steady winds that sweep instead of scour. The lines were preserved. They engineered the skin of the desert to resist erosion for over 2,000 years. This was a project of long-term planning, staggering, really, done for a purpose we can only guess at. Ritual pathways, astronomical calendars, offerings to gods in the sky. The intent is lost, but the scale of the change to the landscape is still here. It makes you wonder what other cultures were willing to reshape their whole world, not for art but for survival, against something even more relentless than the wind. Easter Island, Rapa Nui, it's a speck in the Pacific, one of the most isolated places, and on its slopes the moai, those huge stone faces looking inland. They average 13 feet tall, 14 tons. The largest one ever tried, left unfinished, is over 60 feet, maybe 270 tons. They were carved from volcanic rock at a central quarry. Then they had to be moved. That's the puzzle. They needed to travel up to 11 miles across hills to their platforms on the coast, the Ahu. No wheels. No large animals, just people on an island with limited resources. So how did they walk? There have been theories. One idea was to lay them down and roll them on logs. But that method uses up timber fast, and it's hard to control a multi-ton cylinder on rough ground. Another theory is a rocking motion, using ropes to tip the statue side to side, walking it forward. That's been shown to work with a replica, but scaling that up for the biggest moai, over miles, the risk is enormous. One slip could shatter everything. Maybe the clue is in the roads. The old paths from the quarry aren't flat. They're V-shaped or have a trough, so some think they walked them upright. A slow, swaying procession. The statue kept vertical, pivoted on ropes, guided along the path. A ceremonial dance. The true method might be lost, but the feat itself, it's a profound communal effort. A staggering investment of time and belief. to move a mountain piece by piece across an island. It's a testament what a culture can do when its vision is fixed on one monumental goal. That drive to create meaning from the earth, to orchestrate immense effort for a purpose, it wasn't just happening on remote islands, it was happening underground too. In vast hidden networks built for an empire. Under Cappadocia in Turkey, there's this place called Derinkuyu. It's not a cave, it's a city, but it goes down. 18 levels deep, a whole maze of tunnels, rooms for living, stables, churches, storage. It could hold up to 20,000 people, and that's the first problem. That many people underground, sealed in, they'd use up the air in hours. They'd suffocate, so the builders, they solved that. They engineered the air itself. The city has more than 50 ventilation shafts. Some go down 250 feet. They link the deepest parts to the surface, but they're not just holes. They were placed precisely. They used the natural convection currents of the earth. Cool air would sink down some shafts. Then, warmed by people and their activities, it would rise up through others. A constant passive circulation, a natural air conditioning system running on physics. They also built these huge, circular stone doors, wheels of rock that could roll across tunnel openings and seal them. That let them control the airflow, isolate sections, defend the place, but the knowledge that took, they carved this in soft volcanic rock, tough. It's workable but unstable. To carve that deep without collapses meant understanding load-bearing pillars, the geometry of arches, how stress moves through stone. They did this without geological surveys. Without engineering software, they learned by doing over generations. They understood their material. This wasn't just digging a hole. It was sculpting a functional, breathable, defensible ecosystem from the living rock. A masterpiece of environmental engineering, and it stands in contrast to another ancient approach, where Derinkuyu mastered air underground. Another civilization mastered moving water across vast, open distances. Water flows downhill, that's just how it works, but to make it travel 50 miles under a desert with no pumps at all, that's something else, that's genius. In ancient Iran, the Persians looked at this dry land, a place where life was hard, but they saw the mountains in the distance with snow on them. They knew the water was there, held in the ground. So they built the Qanat, a work of invisible engineering. It starts with a mother well, dug deep into the foothills to reach that water. Then, with hand tools and a sense of direction, they dig a tunnel. A gently sloping tunnel from the water source all the way to where they lived. The slope was critical. If it was too steep, the water would move too fast and wear away the tunnel. Too shallow, and it wouldn't move at all. They needed a perfect grade, sometimes just a 1-meter drop over a whole kilometer, and they kept that precision over distances longer than our highways. They did it without modern tools, no levels, no lasers. They used gravity to guide them, probably with weighted strings and poles. What you could see from the surface were the shafts. Vertical shafts dug down to the tunnel at regular spots. These let in air, helped with digging, and gave access for maintenance for centuries. This was a community effort kept up over generations. One Qanat could support an entire oasis, a city, farmland. It was sustainable. It drew from the aquifer's natural refill, so it didn't use it all up. And because it was underground, the sun couldn't evaporate it. The technology fit the place perfectly. Empires were built on this steady water. It was a quiet foundation for everything. And it makes you wonder now, how do you handle a crucial resource not by forcing it, but by understanding it, by being patient and precise? Their answer was to guide water across huge distances. But then, what about the opposite problem? Not bringing water to people, but shielding people from water, from its sheer, overwhelming force. The Roman aqueducts. We think of them as those great stone bridges crossing a valley, but that's just the part you see. The real work is in the slope, getting water from a mountain spring to a city 50 miles away. You have to let gravity do it. The Romans built these channels with a constant, gentle downhill grade, sometimes just a foot of drop for every 1,000 feet forward. Less than 1 degree, over miles and miles, that's the precision. If the slope is too steep, the water moves too fast. It tears the channel apart. Too shallow, the water just sits. It fills with silt. They had to get it exactly right, and they did this without any of our tools, no lasers. They used something called a corrobates. A long, leveled trough of water. They'd sight along it, check the land step by step. They tunneled through mountains, those arched bridges over valleys. They weren't for show. They were to keep that perfect downhill line. The water flowed in a sealed channel, covered to keep it clean. It became a constant utility. The life of their cities, for fountains, public baths, sewers. It set a standard for public health, for how a city could live, that wouldn't be seen again for 1,000 years after Rome was gone. Their achievement was making the incredible seem simple. A silent river guided by stone and geometry, engineering for daily life, for civilization itself. But that control over the physical world, it makes you wonder, what if you took that same precision, that same focus, and applied it not to water but to stone? Not for a city's thirst, but for a temple built to track the sky. Stonehenge is a circle of stone out on the plain. The big stones, the Saracens, they're local. They make the main ring, but inside there are smaller ones, a blue-gray color. Those are the Bluestones, and they aren't from there. Their rock matches the Preseli Hills in Wales. That's over 150 miles, across rivers, forests, hills. This was 5,000 years ago, the Neolithic. Each stone weighs up to 4 tons. Not the biggest, but the distance, that's what makes it a puzzle. Why that much effort? They weren't for holding anything up, not like the Saracens. Their purpose was different, ceremonial, probably, spiritual. It was a choice about meaning, not engineering. Maybe the stones themselves were sacred, thought to have power from that far-off place. So the journey was part of it, the act of moving them, that was the ritual. But then how? How did they move them? That's where people try to recreate it. Experimental archaeology. One idea is a land route, rolling them on logs, a team levering them along, moving the logs from back to front. Slow work, grueling, months of it. Another idea is water, dragging them to a river, putting them on rafts, sailing along the coast, then up a river. Seems easier, but the sea part dangerous with that weight. Unstable. There's even a thought that glaciers brought them closer during an ice age, and people just moved them the last part, but the geology points to people. Human transport. What gets you is the scale. It means a society that could organize, leaders who could coordinate hundreds of people for a project that gave no food, no shelter. Just a symbol, a shared belief that's strong enough to move pieces of a mountain across a country. That drive to put stone in line with the sky, to haul meaning like that, it finds an echo somewhere else. Another ancient wonder where the stones weren't just placed, they were made to sing. Stonehenge stands there, silent, a calendar in stone, but across the world there's another place. Angkor Wat in Cambodia, it's a temple, but it's also more than that. It's a map of the cosmos built from stone. The size of it is hard to grasp, the biggest religious monument anywhere. But the real achievement is how it's placed. The whole complex is aligned with the sun, with the spring equinox specifically. On that morning, you stand at the western gate. You look back down the main causeway. The sun comes up right over the central tower, a perfect line built into the foundations from the start. To do that, the builders, the Khmer, they faced a problem. They had to anchor this huge structure over a mile square to one point in the sky, a point that only appears one day a year. They didn't have telescopes. They didn't have accurate clocks. They watched the sun for generations. They marked where it rose and set on the horizon. They understood the seasons, that slow change. And they turned that knowledge, that celestial knowledge, into geometry, into lines on the ground. So the central tower, it isn't just a tower, it's the axis. The center of their world, the walls around it, the moat, the long causeways, they're all placed to frame that sunrise. It was engineering, but as an act of faith. A way to tie their sacred ground to the movement of the sky. That harmony between building and the stars, between earth and sky, it's an idea that travels. It shows up again far away in the Americas, where another civilization did something just as staggering, not by aligning with the heavens, but by challenging the earth itself. The sky was their calendar, the lake was their garden. Tenochtitlan, the Aztec capital, it was built on an island, but it was more than that. It grew from the water. Lake Texcoco, it was shallow, marshy, salty in parts, not an easy place to build an empire, so they didn't fight the water, they worked with it, they invented the Chinampa. An artificial island, but that's too simple. Think of a long, narrow rectangle, maybe 300 feet by 30. They'd stake out the shape in the shallow lake bed with woven fences. Then they'd layer it, mud from the bottom, rich with organic matter, aquatic plants, more mud. They built these plots up until they sat just above the waterline. The sides were reinforced with living trees, their roots knitting the soil together, preventing erosion. But the clever part was the canal. Between each Chinampa, a narrow channel of water. And that water wasn't just for canoes, it was part of the farming system. The porous lake bed let water seep in from below, keeping the soil moist. The canal water reflected sunlight, creating a microclimate. They could get up to 7 harvests a year on one plot. Corn, beans, squash, flowers. It was unbelievably productive. This was more than farming. It was integrated design. The canals were roads. The Chinampas were neighborhoods and farms, all woven together. They managed the salinity with dikes and freshwater aqueducts. They created a balanced, self-sustaining ecosystem. It fed a city of perhaps 200,000 people. To replicate that today, it isn't just about a floating garden. It's about recreating that entire relationship, the hydrology, the soil science, the biology inside a living city on the water. It's engineering that doesn't impose a grid on nature. It learns nature's language. It builds a conversation. That idea, carving a civilization from an unforgiving landscape, creating life where it seems impossible. It finds its most extreme expression not in a lake, but in a cliff face. That conversation with the landscape, it finds its purest form in a city carved from the inside out. Petra in Jordan. The architecture there wasn't built. It was revealed. The Nabateans, this desert people, they didn't haul stones to a site. They approached a cliff of rose-red sandstone, and they saw the building waiting inside it. Their most famous creation is Al-Qasne, the treasury, a facade 40 meters high of staggering beauty, but it's not a structure attached to the rock. It's the rock itself sculpted. This is subtractive construction. Every column, every statue, every delicate urn at the very top, all of it was created by removing material. They started at the top of the cliff and carved downward. You have to imagine the confidence that requires. With additive building, you place a block. If you make a mistake, you can replace it. Here, every strike of the hammer is permanent. Chip away too much in the wrong place, and the entire vision is ruined. So their engineering was about control. It was about understanding the stone's grain, its weaknesses. They carved drainage channels right into the facade to divert rainwater, preventing erosion that could undermine their work from the very beginning. Inside, they hollowed out chambers, tombs, and halls, always mindful of leaving enough solid rock to serve as pillars, to serve as roofs. This was architecture as an act of profound faith. Faith in their own skill and faith in the mountain's strength. They worked with the natural fissures in the stone, using those fissures to guide their excavations. The result feels both monumental and intimate, like a secret pulled from the heart of the earth. That approach it stands in stark contrast to the next ancient feat, where the challenge wasn't revealing a form within, but assembling perfection from countless separate pieces. Petra came out of the mountain, but then there's this other place. It's almost the reverse, a city built on the water, Nan Madol. It sits on a reef off Pohnpei, just a ghost of it now, over 90 little islands man-made, with canals between them like waterways, but the building material, that's what gets you. The walls are made of basalt logs. These are natural columns. Volcanic rock formed into these long, hexagonal shapes. Each one is a giant stone beam. Some weigh 50 tons, and they're stacked like a log cabin but in stone. Walls go up 25 feet. The size of it is hard to take in, and the location makes it a puzzle. The basalt didn't come from there. It came from the other side of the island. So first, how did they move these stone logs across land, then over open water to a reef with no real harbor? They had no metal, no pulleys, no wheels. The main idea is they used rafts, huge bamboo rafts tied together. Maybe they floated the stones out at high tide, guided them with canoes, but imagine that. A 50-ton rock on a raft in the open ocean. One big wave and it's over. Then there's the stacking, lifting these multi-ton logs, placing them just right. Without cranes, that points to leverage, and maybe they use the tides, build an enclosure, float a stone in when the water's high, then let the tide go out. The stone settles into place. It would have been a slow process, a kind of rhythm with the sea, a project that needed a whole society working for generations. What it was for, that's still part of the mystery, probably a ceremonial center for the ruling class, a place set apart on the water to show power over both land and sea. To be there, you feel that ambition, this huge weight balanced on the waves. It's a monument to patience, to step-by-step genius, and it makes you think what other ancient people knew their materials so well. It feels like it shouldn't be possible yet. The sea holds the weight of stone, but the air holds a different test, corrosion, time's slow hunger for metal. In Delhi, there's an iron pillar. It's been standing for over 1,600 years. A solid shaft of wrought iron, 23 feet tall, 6 tons, forged in the 4th century as a tribute to a king. But the legacy isn't the inscription. It's the surface. After all those centuries, after monsoons and sun and city air, it shows almost no rust. That's the mystery. Modern steel left outside would be gone in a fraction of that time. But this ancient pillar is nearly pristine. The secret is in the recipe. Modern analysis shows a very high phosphorus content, very low sulfur and manganese. The opposite of industrial iron, this unique mix with Delhi's specific dry and wet cycles allowed something to happen. A thin, protective film formed. A passive layer of iron hydrogen phosphate. It's stable, it adheres tightly, it doesn't flake off, and if it gets scratched, the local climate helps it heal. The film reforms, it's a self-protecting skin. Now, the question is whether this was intentional genius or a happy accident of their smelting. The iron likely came from a bloomery furnace using high phosphorus ore. The craftsmen would have known this iron was different, easier to forge, maybe more resistant. They might not have understood the chemistry, but they recognized a superior material. To replicate it today isn't just about matching the formula. It's about recreating the entire ancient process, the specific ore, the hand-forging techniques, and then exposing it to that exact climate for centuries. It represents a lost branch of material science, where the impurities weren't flaws, they were the key to immortality. This mastery over metal, creating something that defies time, points to a deeper understanding, where the material wasn't just durable. It was designed to manipulate the fabric of the world. The iron pillar in Delhi is a record of patient chemistry. Then, centuries later and continents away, there's another metal object. It tells a different story. A story of lost urgency, forgotten fire, the Viking Ulfberht swords. These are weapons from a brutal time, the early medieval period, about 800 to 1,000 years after the Common Era began. But their quality is a quiet shock because most European swords then were brittle. They were made from impure iron and they could snap in battle. The Ulfberht was different. It was flexible, it was strong, it could bend and then spring back to true. The secret was the steel. Modern metallurgists have analyzed the blades. They found it was crucible steel, a high-carbon steel of remarkable purity. To make it, you melt iron and carbon together in a sealed clay crucible. You need extremely high temperatures. That process burns off impurities like slag. It creates a uniform metal, a homogeneous metal, so the blade is hard enough to hold a sharp edge, but also flexible enough to withstand an impact. The puzzle is this technology, this level of purity. It wasn't seen again in Europe for centuries. It just vanished. So where did it come from? The leading theory points east along the Viking trade routes to the Islamic world, where they knew crucible steel production. Places like modern-day Iran, Central Asia. The raw material might have been imported as ingots, then forged by Norse smiths who inscribed that name, Ulfberht. Or maybe Norse craftsmen traveled. Maybe they learned the technique themselves. But the specific smelting recipe, the exact temperatures and timings, the flux materials used to draw out impurities, those details are lost. It's a fleeting peek of ancient knowledge, a brief window where the art of the forge reached a perfection that wouldn't be common again until the Industrial Age. It reminds you that progress isn't a straight line. A craft can ascend to brilliance and then, through war or broken trade routes or the loss of a single master smith, it can fade back into the earth. From that intense, focused fire of the forge, we shift to something else, a cooler, more geometric marvel, one that required a different kind of precision. Working with stones so large their movement seems to defy any simple explanation. The Ulfberht swords were a moment of perfection in metal, but for stone, on a scale that's even larger than a Viking ship, you look to Lebanon. To Baalbek, the Romans built a temple complex there of staggering size, but the real wonder isn't the temple on top, it's what's underneath the foundation. 3 limestone blocks, they're called the trilithon. Each one is about 64 feet long, 14 feet high, 11 feet wide. The weight is almost impossible to grasp. Around 800 tons, that's heavier than 2 jumbo jets fully loaded, and they're not just placed there, they're fitted together with precision. A level base for the walls above, that alone would be a record, an ancient engineering record, but then you follow the trail. Half a mile away is the quarry. And there, still in the bedrock, is the stone of the pregnant woman. A single block cut, estimated at over 1,000 tons. It was never moved. It's like the builders were testing a limit. And this was the step too far. So how did they move the others, the slightly smaller ones? The distance isn't huge, but the weight is from another world. Theories mention a system, enormous wooden sledges, rollers, levers, thousands of workers, oxen pulling together. They might have built a temporary road. Reinforced the ground to take the pressure, but even with all that, the coordination, it's hard to imagine. One misstep, one snapped rope, and the project is over. The stones are so large that modern cranes that can lift them are rare. They'd struggle on that ground. The Romans left no manual, they just left the stones, silently holding up the temple, as if to say the method was obvious: leverage, manpower, will. But when you stand there, that explanation feels thin. Incomplete. It feels like watching a physical law bend, gently, a demonstration that ancient willpower, focused, could make the earth itself a building block. And that ambition to command the weight of the world, it wasn't just in the Mediterranean, it echoed across an ocean, in a culture that didn't just move mountains. They fit them together like a puzzle, a cosmic puzzle. The stones at Baalbek feel like a statement of power, a statement of sheer weight, but across the Atlantic there's another ancient culture. They worked with the same heavy material but for a different purpose. They carved faces, colossal faces staring out from the jungle floor. These are the Olmec colossal heads. The first great civilization of Mesoamerica. Each head is a single block of volcanic basalt, a stone so dense, so heavy, it seems to defy movement. The largest ones stand over 9 feet tall. They weigh close to 50 tons. That's the weight of a fully loaded semi-truck, and that's just the finished sculpture. The raw block they started with was even heavier. Now the journey. The basalt came from the Tuxtla Mountains, quarried from the slopes of ancient volcanoes. The final sites, like San Lorenzo or La Venta, are over 60 miles away. Through a landscape that is not cooperative, dense tropical forest, swampy lowlands, rivers that flood, there were no wheels here, no metal tools to cut a smooth road. And critically, no draft animals, no oxen, no horses to help pull. Every ounce of that 50-ton mass was moved by human hands, human ingenuity, human will. So, how do you move a mountain when the mountain is a single stone head? The leading theory involves a system of rollers made from the abundant hardwood trees. They would have levered the raw block onto a wooden sledge. Then, teams of hundreds, maybe thousands, would pull with ropes. Others would constantly reposition the rollers from the back to the front. It's a slow, rhythmic, grueling process, a few feet per hour at best for 60 miles, but the terrain adds another layer. The swampy areas suggest they may have used rafts, floating the stones along rivers when possible. This wasn't a straight-line haul. It was a logistical puzzle, solving each obstacle, a steep hill, a wide river, with the materials at hand. The coordination needed is staggering. It speaks of a highly organized society, one capable of mobilizing a workforce for a project that offered no immediate practical reward. These were not tools or weapons. They were portraits, likely of rulers. The act of moving the stone, of carving it into a lasting likeness, was the act of creating power. Creating legacy. It was a communal sculpture. The labor of thousands became the immutable face of one. That ability to organize on such a scale, to direct human effort toward transforming a landscape not for survival but for symbolism. That finds its ultimate expression in one final, breathtaking project. A project that didn't just move stones or carve faces. It etched a message across the very skin of a continent. The Olmec heads showed what a coordinated society could do, but to maintain that effort, to extend it across centuries, across an entire empire, you need something else. A different architecture, not stone but systems. That brings us to the 19th feat, the Great Wall of China. We think of it as one long, unbroken line. But that's not true. It's a patchwork, different walls, built and rebuilt by different dynasties over 2,000 years. The famous stone sections are from the Ming dynasty. But the real foundational work, the one that changed the scale of what was possible, came much earlier, under the first emperor Qin Shi Huang in the 3rd century BC. His vision was absolute, to link the old walls into one continuous barrier, a statement of unity, but the reality was a logistical nightmare. This wasn't just building a wall. It was building a civilization along a line. They had to move millions of people, conscripts, soldiers, prisoners to the frontiers, and these weren't normal sites. They were remote, hostile mountain ridges, deserts, places with no water, no food. So before any construction could start, they had to invent a support network. The supply chain alone, feeding an army of workers stretched over thousands of miles. Grain had to come from the south, carried on carts over roads that turned to mud. Water had to be found or carried into the dry zones. The materials dictated the design. In the mountains, they used local stone. On the plains, they rammed earth between wooden frames. In the Gobi Desert, where there was no stone or good soil, they used what they had. They mixed sand and gravel with layers of reeds and willow branches. That made a stable, flexible composite that could hold against the wind. But the real genius was management. How do you command a project that vast without modern communication? They used beacon towers built ahead of the wall itself, watchtowers on high points within sight of each other. They weren't just for invasion alerts. They were an administrative network. Messages could be relayed across the empire in days. Requests for supplies, progress reports, orders from the capital, all flowed along this line of sight. It was the nervous system of the project. The human cost was immense, woven into its length. Historical accounts describe the hardship, yet its legacy isn't just that struggle. It endures as a physical form of organizational genius. It proved an ancient ruler could conceive of something on a continental scale and could develop the systems, the supply routes, the material adaptation, the communication lines, to make it real, however brutal the process. It stands as the ultimate ancient mega-project, a lesson in long-term logistics that still staggers the mind, and it sets the stage for the final entry. Because if the Great Wall is the peak of coordinated, monumental effort, something we can see and touch, then the last feat is the opposite. A coordination so subtle, so precise, so advanced that we can barely detect it. It exists not in stone, but as a ghostly imprint on the land, pointing silently at the stars. The wall was a statement of human coordination on a continental scale. But the last ancient feat asks something more basic. What if the very first monumental coordination happened for a reason we've lost? What if it wasn't the end result of civilization, but the thing that started it? That question is carved into a hill in southeastern Turkey, Göbekli Tepe. It's not a city, it's not a fortress, it's a series of circular enclosures built from massive limestone pillars shaped like T's. Some are 16 feet tall, they weigh over 10 tons. They were quarried from a ridge nearby, shaped and dragged to the top of the hill, and then they were decorated with intricate, beautiful reliefs, foxes, cranes, scorpions, lions, a whole menagerie of wild animals frozen in stone. The date is what stops you. This site was built around 11,600 years ago. That's 7,000 years before the Great Pyramid. It predates Stonehenge by 6,000 years. It was built by people who, by our traditional story, should have been simple hunter-gatherers. Nomads following herds. They had no agriculture, no permanent settlements, no pottery, no metal, and yet they organized, they gathered, they planned. The scale of labor is staggering. To quarry a 10-ton pillar from solid bedrock using flint tools, to shape it into that T-form, to transport it, probably with log rollers and ropes, up to the hilltop. And then to erect it, standing it upright in a prepared socket, aligning it with others in a perfect circle. This isn't the work of a family band. This required hundreds of people working together over months or years. They needed to be fed, housed, directed. That implies a social structure far more complex than we ever imagined for that time. And the purpose, that's the deepest mystery. It wasn't a dwelling. There's no evidence people lived there year-round. It seems purely ceremonial, a sacred space, a gathering place for rituals we can only guess at. The pillars themselves might represent stylized human forms, the crossbar being the shoulders, maybe ancestors or gods watching over everything. This turns our historical timeline upside down. We always thought monumental architecture was the product of settled, farming societies. That agriculture created surplus food, which allowed for specialization, which then enabled grand projects. Göbekli Tepe suggests the opposite. It suggests that the drive to build something monumental, to gather for a shared spiritual purpose, came first. That this collective endeavor, this need to create meaning together, might have been the catalyst. The cooperation required to build Göbekli Tepe could have taught people how to organize for other tasks. It might have planted the very idea of a settled community. So here we are at the end of the list. We started with the polished perfection of the pyramids, a high point of ancient state power, and we end here at the raw, awe-inspiring dawn of something new. A hilltop where hunter-gatherers decided to carve their world into stone, and in doing so, perhaps carved the first blueprint for civilization itself. Each of these feats, from the self-healing iron to the celestial temples, from the underground cities to the mountain-moving statues, they share a common thread. They are not just relics of what was lost, they are profound questions asked in stone and metal and earth. They challenge our arrogance about progress. They whisper that genius is not a product of our tools but of the human mind, of observation, of patience, of a deep dialogue with the natural world. Our ancestors looked at a mountain and saw a temple. They looked at the stars and built a calendar. They looked at a desert and drew a message for the sky. They solved problems we still struggle to replicate, not because they knew more than us, but because they knew differently. They remind us that history is not a straight line from primitive to advanced. It is a tapestry full of brilliant, forgotten peaks, and the greatest mystery they leave us with isn't how they built these wonders. It's what we might build if we ever learn to see the world as they did. That legacy is really what ties these 20 wonders together. It's not the pyramids or the pillars themselves. It's this pattern of human ingenuity that doesn't fit our simple timelines. Self-healing iron, a temple aligned with the equinox sun, these aren't accidents. They're the result of sophisticated knowledge, deeply specialized knowledge. And that knowledge was sometimes lost, sometimes forgotten, because it lived in the hands of the craftspeople, not in a library. Our ancestors observed their world with a clarity we can struggle to match. They saw patterns in the stars. They understood how water flows through stone. They learned the hidden strengths in materials we now take for granted. And they manipulated their environment not by overpowering it, but by working with its rules. That challenges the whole linear idea of progress, the idea that we're always moving forward, that newer is better. These ancient marvels are proof. Innovation isn't a modern invention, it's a human trait. Genius has flourished in every age given the right conditions. Need, belief, communal effort. And now, as we study these sites with new tools, ground-penetrating radar, molecular analysis, we're doing more than solving puzzles. We're mining the past for inspiration. The passive ventilation of Derinkuyu could inform energy-free architecture. The earthquake-resistant masonry of the Incas might teach us to build more resilient cities. The sustainable aquaculture of the Aztec Chinampas offers a model for future food. These aren't just relics, they're prototypes tested by time. They remind us that the most advanced solutions might not lie ahead of us. They might be behind us, waiting to be seen with new eyes. So what other secrets are buried in a forgotten manuscript or beneath desert sands, waiting to reshape what we think humans can do?